se lo copio a los americanos.
Tú te lo guisas, tú te lo comes, ¿eh?
Lo cual no hace falta que lo hagas un súper detallado si no quieres. Si lo haces más detallado, me salta esta.
Vale, lo que quieras. Lo que tú prefieras. ¿Qué prefieres? ¿Presentarte a ti mismo o que te presenten?
Me da igual la frase. Esto es... No vas a decir todo esto, con lo cual...
Vale, si quieres presentarte, yo digo tu nombre. Pero...
Vale.
Carlos García-García.
Y que se va a autopresentar, ya está. ¿Tú estás puntero? Sí, puede ser.
No necesitas ser. La verdad que no.
Es un poquito débil. Es una luz real.
¿Es este lo que ahí? Sí.
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 Los últimos.
Bueno, por pasar eso ahí está.
Eso es.
Comparado con el
Sí, micrófono entiendo que no. Micrófono atrás.
del golf.
No creo que tenga que estar al fondo. Vale. Ok.
Nada, ánimo. Vale, gracias.
Sí.
Por favor.
Nada como un día y sí, que suena.
La primera. Son interesantes. Pasa mucho rato.
Bueno, pero eso
Y
es
esto,
de gusto.
Javier,
Así, pero pues
ahí apagas. Y la comisión.
vamos a venir con más gente. No tengo dudas. ¿Cómo? Ah, vale, es que me inventaba antes de empezar. Bueno, gracias. So we are here. So today we have here Carlos Garcia-Garcia. He's going to do his presentation himself because he has prepared a slide for it. So thank you, Carlos.
Okay, thank you for the nice introduction. So thank you for inviting me to give the talk here. It's the last time I was here, that was like 2 years ago when Raul prepared this conference, and I ended up swimming in the Cantabric at night, accidentally. No, it wasn't super fun, but yeah. So yeah, just to start with why I copied this from the Americans. So I studied in my undergrad in Madrid in the Complutense, and then I did a theoretical master physics in also the Complutense. Then I moved to, well, I was between Barcelona and the SIC in Madrid, doing my PhD on modified gravity phenomenology. And then I started after the PhD, I started as a Bicrot fellow in the University of Oxford, and now I'm moving next month to Waterloo as a WCA fellow in Canada. My interest in cosmology is as a way of learning something about fundamental physics. And that's why I did a PhD basically on darkening and modified gravity phenomenology. And now during the postdoc, I'm doing more like large-scale structure data analysis. And in particular, very involved in LSST, where I got the builder status after many years of work. And I had different leadership positions on them, like leading the tool that computes the covariance for the angular power spectra. I was also convener in the weak lensing and large-scale structure working group. And now I am the responsible of the CCL, one of the responsible persons in the CCL and fine-ground topical team that is in charge of the theory prediction. And I'm also a member of Euclid, although I don't have the time that I would like to also spend too much time in Euclid, and I mainly engage with the people that are doing covariances there. So going to the science, as I said, I'm interested in cosmology because I'm interested in understanding something about fundamental physics. And my goal will be to understand what is dark energy. So since the 1998, when the HISE supernova search team and the supernova cosmology project detected that the universe was expanding accelerated using the supernovae as standard candles, we know that basically the universe, well, they detected that the universe needed to have like some form of dark energy to explain that accelerated expansion at the 7 to 8 sigma level. But it was not until 13 years later, after there were many other observations confirming that they got the Nobel Prize for this discovery. So, for instance, here I'm showing the amount of dark energy versus omega matter. And you can see that the measurement that they did with supernovae is basically in this blue contour. But then you also had complementary and independent measurements from, for instance, baryonic acoustic oscillations, that basically you measure how the sound scale changes over time. And also from the WMAP of the anisotropies on the temperature fluctuations in the universe. And by having these three different and independent measurements, you see that basically the universe predicts to be flat, that needs clearly something that is about 70% of dark energy in the universe. So it was like 13 years since the first hints of first discovery of the accelerated expansion until the community was convinced enough so that they got the Nobel Prize. And actually, the standard model fits very, very, very well the data. And so here, just the angular power spectrum from Planck 18. And as you can see, basically the theory prediction in blue fits very, very well the data points. And this is just the standard model with the 7 free parameters. However, 2 years ago, DESI reported something different. We are, at the moment, at DESI measuring the baryonic acoustic oscillations together with the CMB and the supernovae from different surveys, detect that maybe the dark energy is not constant, maybe it's not a cosmological constant, maybe it's changing. And they say that basically there might be dynamical dark energy favored by 3-4 sigma. So we might be at this stage of like before in 1998, and now we need just more and more probes to convince ourselves that this is real. And so here we see the equation of state parameters, W0, WA. This is a specific parameterization. The equation of states basically is a phenomenological way of describing how the homogeneous universe evolves, basically how it expands. And basically the idea is just you have just 2 free parameters that change, that basically tell you something about its value today and kind of its slope. But you can also have something that is even more general. You have a Gaussian process, as they did in the DESI collaboration. And then what you see is that the equation of state at early times on the right, it wants to be in the phantom region. It wants to be like lower than -1. With a phantom crossing here, that goes to values of the equation of state larger than -1, where -1 would be the result for the cosmological constant. So the result of dark energy of this 3-4 sigma evidence towards dynamical dark energy is not just parameterization dependent. It's actually something that the data is showcasing. The question is what we can learn from this. What we can learn from phenomenological description about the dark energy properties. And this is something I've been working on with collaborators there in Oxford, and I will show you the results that have been mainly driven by this guy here, William Wolf, that he was a former PhD student of Pedro Ferreira, that I helped to co-supervise, and these other 2 postdocs, Declan Bartlett and Theo Anton. So the ultimate goal as a theorist would be to find the Lagrangian, the action that describes dark energy. And then we can think of W0, WA as a way of compressing our data. Just to have an idea, this is something that I started working in the PhD, and then they improved in 2 recent papers. If the ways will be like you have your data constraints, and then without the need of running an inference, a full inference that is costly, especially taking into account that there are hundreds of different models, you should be able to project the theory, the phenomenology of the theory onto this space. And then you could say, if the contours of the theory do not overlap with the data contours, that's going to be a bad fit to the data. And if they overlap, then in this case, they will be a good fit. Then you can just focus on the theory 2 instead of theory 1 when you do the full inference or you have to run simulations. And the way that this works is the following. You start from your Lagrangian, as you would do like if you do a full inference. You generate a sample of parameters within the Latent hypercube for the parameter ranges that you think that are physically sound. And then you compute the observables of interest, that you're basically the same observables that the data you are using require. And then the key part is that you try to obtain WWA that fits that observables. And the key part that Pedro and Will realized 2 years ago is that instead of trying to fit perfectly well these observables, like you will do in an emulator, trying to reproduce exactly the observables, what you do is like you weight these observables by the errors that you see that your observations use. And that way you can compare the contours of the data and the contours of your theory in a fair basis. You're basically proving the same observables with the same weights. In this case, you are not fitting WA is not a Taylor expansion, nor is a fit to the equation of state. In this case, you have the equation of state here, for instance, for the scalar field in black, where the present is on the right. And then, depending on what data you are going to be comparing your WA contours with the data, you will have different predictions. You will have different fits. So, for instance, in the case, let's focus first on CMB. You have something that is very much flat. And this is because CMB is putting a strict prior or a strict measurement on the angular diameter distance at very early times. And basically the first peak of the of your angular power spectrum, the temperature fluctuations. However, in the case of the supernovae that are much more low resifs, you find something that is fitting better. It's not a fit, but it's like it resembles more like the equation of state at early times. So you do this for all your lighting hypercube, and then you can just project it to the WA space. And in this case, I'm showing here the projected models, 3 different models that have very different Lagrangians. They have very different number of free parameters. And we checked that basically you can compress the whole phenomenology in these 2 parameters. And by doing the fitting that I showed you before, you can put them in this plane. And what you see is that 3 different models with very different Lagrangians, with very different number of parameters, they predict that they overlap in the same region. If this WA parameter is actually a good representation of your phenomenology, that we check that it is, then this means that basically they are all predicting the same changes of in the observables. So basically that means that your cosmological data will not be able to observationally distinguish them. But then the question is, if we are not going to be able to distinguish these different models, we are not going to be able to distinguish, to pin down the full Lagrangian of our dark energy model. So the question is then, what are the minimum properties that we can learn from dark energy with cosmological and current data? And in order to answer these questions, I will assume 2 things. The first thing is that the data that we are going to use is correct, because that's just an operational thing. There might be an error, and that all the things that we are seeing now is just some systematic that had not been accounted for. But let's assume that the data are correct. The second thing that I'm going to assume is that dark energy is going to be driven by a scalar field. That's the simplest extension from a cosmological constant. If we assume that the dark energy is going to be driven by a scalar field, it can be shown, as it was shown in this paper, that at the lowest order EFT, the action of your theory is given by this action here. If you set F to 1 and K and the potential to 0, you recover general relativity. But if you have a scalar field, you have these free functions of the field that are completely free. Because there is too much freedom, we do a further step trying to simplify the problem. That is, Taylor expand these different free functions in a Taylor expansion on the field. And we can do this because a posteriori we see that the change on the field is very small when you do the full evolution of the field. And then we focus on 3 different cases. And this is not like, we are not trying to see what model fits better the data. We're trying to explore 3 cases that will give us some meaningful information about the properties, the microphysical properties of the field. So we focus first on a case that we call the Zoe model, that basically is a minimally coupled field to gravity. So this is 1. You have a standard kinetic term, and then you have a potential that we expand up to 2nd order, so we can say something about the mass of the field. The second case that we look at is a case that the field is non-minimally coupled to gravity. In this case, we Taylor expand F up to 2nd order. We keep a standard kinetic term, and then we expand the potential up to 2nd order. And the last case we explore is what happens if you don't have a standard kinetic term. So we expand K up to second order as well. And this way, we will be able to say something about the mass of the field, its possibility to be coupled to the gravity, and if it has a standard or non-standard kinetic sector. And this is what we found in the WNWA plane. So the data is in the gray. And we see that, for instance, the minimally coupled field that expands this area here will not fit the data very well. So we don't, just the standard, the easiest extension is not preferred by the data.
Sorry, Carlos.
Yes.
Again, I might have missed something, but don't you have degrees of freedom in your minimal?
Yes.
Scalar field case?
Yes. Let's see if I can. No. So yeah, in the minimally coupled field, that would be what I call throwing here. You have this parameter is free and this parameter is free.
But
So
it doesn't change the equation of the state. So why is it a single line?
no, it's, sorry. Yeah, this is this area between. So basically, what I'm showing here is the area that expands, that the model can expand. I'm not showing a contour as before. It's more like the theory will expand all this area here in this space. And the same for it's more clear in the blue. The blue and the red will expand all these areas.
So could you give us an intuition of why there are some area that is excluded?
Why this area is preferred?
For instance, in the minimal phi case,
Yes.
so why the W0 minus 0.6 WA0 is excluded?
This area here.
Yeah, for instance, why that's not possible?
That's I mean, in this kind of models, for instance, your equation. If you look at the equation of a state, you only have just like constant at some point. There's because that's why we got throwing. The field is frozen and then it slowly starts rolling. So you don't have that much freedom on and that's also why the three models that I showed you before, they all lie on the same place, because regardless of the amount of parameters you have, in the end, you always have the field is frozen and then it starts rolling. And then you don't have that much freedom to do with that. So that's why it's within a very specific region. Whereas for instance, in the well, let's ignore that one. In the non-minimally coupled field or the symmetrical Galileo, they can start below -1 and then grow to larger values of -1 than -1. So they have like more dynamical range, and then they can expand, make the universe expand a little bit faster to fit the data.
Okay.
I think that maybe not sure if I put a plot of the equation of state, maybe in the backup slides, if you want to show it later.
Oh, okay.
So yeah, so basically the E-simplest extension seems not to be favored by the data. Then in the case that you have I was very studied some years ago, I see Galileo models that have symmetry, they are completely ruled out. And in the case that I mentioned before, the case you have a non-minimally coupled field or you broke the symmetry of the Galileo model, you can actually expand all this area and overlap with the data. But this is just a qualitative statement. So then we focus on these two cases that were able to overlap with the data, and we did a full Bayesian inference, and we computed the Bayes factors. And then we found that there is a strong evidence for both the non-minimally coupled field with Bayes factor 7 over lambda CDM, or the broken symmetric Galileo model with Bayes factor 6.5 over lambda CDM. There is a strong evidence for these models over lambda CDM. That's the point. In addition, we saw that in the case that the data seems to prefer strongly that the mass of the field, the square of the mass of the field, will be negative. That means basically that is rolling down potential. And then the thing is that because you have this coupling or this non-standard kinetic term that produces that has ancillary consequences. And I'm showing here on the left the mu parameter. Basically, it's a kind of way of measuring the strength of gravity over time. You have one would be like what you get in GR, and when you have this extra field, you see that the strength of gravity in this case is enhanced. And of course, that's if you go to plot on the right, when I'm showing the growth rate measurements times sigma 8, sigma 8 is roughly the amplitude fluctuations. You see basically that lambda CDM is in black. The other two models have a faster growth rate. And that will be affecting how much structure you see today. The thing here is that we did not use growth measurements at all because DESI does not have the covariance public yet with the measurement. But that would be something interesting to do. So the thing is that so far we have some of the results that come from mainly the background, the expansion, and linear perturbation for the CMB. But these models will have profound consequences. Like, for instance, you will need a way of making it compatible with local tests of gravity. Basically, there are stringent constraints on how much you can deviate from GR. And then you will need a way of screening this fifth force, this enhanced strength of gravity. And the good thing is that, for instance, the symmetric model might have one built in because you have this non-standard kinetic term. And in the case of the non-minimally coupled model, is still to be seen. That's a computation we have to do. But also, as I mentioned before, you will be changing the large-scale structure of the universe. So it will be interesting to see what happens when you introduce large-scale structure data. For instance, I'm working now in looking at the integrated source-well effects that is proportional to how the potentials change over time. I think that they have recently released the F sigma measurements, DESI F sigma measurements that can with the covariance with BO. So that will be something interesting to do and to check. And of course, in the context of photometric surveys, it will be interesting also to check the galaxy clustering with cleansing, but that's going to be further away. And the question is then, what happens if they disagree? What happens if you introduce your F sigma measurement? And I don't have the plots, but there is a recent paper from a guy in Oxford, Richard Stariek, something like that, finds an F sigma measurement that is very close to the prediction from lambda CDM. So what will happen if I introduce this extra data and you find something that goes back to cosmological constant, to lambda CDM? So I think there are two underlying assumptions in our work. One, that the data are correct. And the second one, that the dark energy is a scalar field. If you find something that disagrees, one of these assumptions might be wrong. It can be that the data are wrong, like DESI or like whatever large-scale structure data I use, or it might be that the theoretical assumption that dark energy is driven by a scalar field is wrong. And that's pretty profound. The problem with using large-scale structure data is that we need simulation, and those are costly. So I will not talk more on that part for now. The alternative, and this links to what I've been doing in the last years in Oxford, is that you can do consistency checks within lambda CDM to guide us, like as extensions, like we've been doing for with cleansing, for instance, or do model independent analysis that can guide us towards what kind of modification we need in the phenomenology, in the model. And this links to the second part of the talk that VS Code is trying to hijack my laptop. Okay. Sorry, I should have closed VS Code. Now, so this links to the second part of the talk and with the work I've been doing all this time in Oxford since I'm going to be a little bit less fundamental physics oriented. So the idea is that if we have this, if we want to use large-scale structure data, before we have to need to believe the constraint in order to do this assessment between tensions and everything, because if the data has been model incorrectly, we might end up just not being guided in the wrong direction. So in order to have robust cosmological constraints, what I think that we need is robust and fast data analysis methods, and also data from multiple large-scale structure probes so that we can test and we can prove our modeling in different regions. So for instance, galaxies will be mainly proving the peaks of the density, matter density, but you can add extra tracers like TSZ or X-rays that might be tracing the gas distribution. So having data from multiple large-scale structure probes will be needed to test thoroughly all the data and maybe to self-calibrate systematics. And now I will be focusing mainly, as I said before, in photometric surveys. Photometric surveys are these surveys that do not observe the spectrum of the galaxy very accurately, but you use broad color bands, which means that you are able to observe much faster the sky. You observe many more galaxies, but you lose the redshift of the. You only have a rough estimate of the redshift. And the two tracers that I will be talking about mainly will be galaxy clustering, basically how the galaxies cluster. And this is because at the larger scales, you can relate it with the density of matter easily with the galaxy bias. And the good thing is that it will give us information about the structure of the universe at the specific times. And in general, if you look at the power spectrum, it gives you information about the scale dependent that it normally translates into the amount of matter in the universe. And the second tracer that we'll be discussing mainly will be weak lensing. That is the second main observable of for photometric surveys. In this case, you observe the shape of the galaxy and try to and how is distorted by the weak lensing effect. So you have the photon that travels to us from the source galaxy, finds some clusters in between, and then it is deflected. Because it is affected by visible dark matter, it's an unbiased tracer. It's integrated because it's affected by all matter, so you lose information about the specific clustering at the specific times. And because it's noise dominated, you need millions of galaxies, so that's why you need photometric surveys. And if you look at the power spectrum, it's very complementary to galaxy clustering because it's unbiased. You can measure the growth, the amplitude fluctuations. Because it's integrated, you lose information about the scale dependence. And in general, you can go to much smaller scales than in galaxy clustering. Although at those scales, you might have to worry about the effect of baryons, the fact that we will have gas distributed and that distorts the predictions from our simulations. Or, for instance, that the galaxies might have an intrinsic alignment due to the local tidal force. Because we have typically because you have lost the redshift of your galaxy, what you do is you have your whole sample and then split it in subsamples in what we call tomographic bits. And basically, you decide some ranges of redshift, and you assign them normally by the rough estimate of your photometric measurement, and then you calibrate the sample against some spectroscopic sample or some more accurate photometric sample like Cosmos. And I'm here showing just the case for LSTIR1 for the lenses, that is what you use for galaxy clustering, or the sources, that is what you use for weak lensing. So, and once you have split it in different tomography beams, you project it on the sky, you mask the region that you don't observe, you mask the parts that have bright stars, etc. And because you work in the sphere, the natural basis will be the harmonic space. You just decompose your field in spherical harmonics and compute the covariance that basically that's going to give you the angular power spectra that looks roughly proportional to 1/L. Roughly, or to some power. And you can relate it to the 3D power spectrum that you normally get from emulators or Halo feeds, things like that, by this limit integral, this integral along the path of sight with two kernels that will depend on the tracer that you are cross-correlating. In the case of galaxy cluster with lensing, we have here the Presi distributions for DSGR1 and the corresponding kernels. And you can see that the galaxy clustering kernels will be basically the same as the kernels of the galaxy clustering will be the same as the Presi distributions. And in the case of cosmic CR, because you have it's an integrated effect, your kernel is basically goes to all the way to zero, and it's a smoother version, this integrated effect. And because you go to all the way to zero, this goes to very high K. This means that basically you need also to be careful with how you model your power spectrum at the smaller scales. So far, we have been good because also the errors of the data scales have been very close. But this will be challenging for the future. And the good thing of having this just full sample subdivided into tomography is that you can do tomography. So imagine that you use what is called filter to point. In the case you use the cross correlation between galaxy clustering and cosmic shear, you will have something that is very narrow with something that is very broad. Then this is going to be roughly proportional to the amplitude fluctuations at the redshift where the galaxy clustering sample is located, times the galaxy bias. But if you introduce the other autocorrelations, then you can actually measure your the evolution of the growth. But in order to do this, especially in the context of LSST-GR10, you will need to have fast data analysis methods. You need something that is going to be fast and something that allows you to combine many different data together. And it's something I've been working on in the last 5 years, even before starting the postdoc. And this is developing this tool that we have called COSMOTHEKA that basically allow us to take all the way from the catalog to the cosmological parameters, or not only cosmological parameters, to some inference. Basically, we are very easily we can produce maps from public catalogs. Basically, this is a very survey-specific step where you have to create the map, project it to the sphere, like mask the region they have not observed, apply the weights, etc. And the key part of COSMOTHEKA is the second step. Basically, the way that we do the statistics. And the key part is that because this step is widely independent from the survey details. So we use an unbiased estimator called the pseudo-CL as implemented in the master. And then the key part is how we estimate the covariance. We use an analytical estimation. We don't do simulations that require a lot of time and computing power. We use an analytical estimation that we have checked that is accurate and is fast. It's called the narrow-Ken approximation. And the good thing is that basically this automatizes the production of covariances between the different angular power spectrum. And then we can combine many different data together. And the final part is that you have a module that interfaces with Covaya, and then we can do the inference for the cases where we can model the signal, like for instance, the weak lensing, we have halo filter emulators or halo model. And this step will depend on the product you're combining. So if you combine X-rays, you will need to introduce a model for how X-rays are related to the matter distribution. And going back to the second point that we need to have robust cosmological constraints, I said data from multiple large-scale structure probes, and this is so that we can test thoroughly that our models fit the cosmology, the cosmology, and the astrophysical models can describe all the probes consistently. And as I showed you in the case of 3 to point, it also allows you to self-calibrate some of the systematic effects. So this is a very cartoonish plot that I should have played at some point. Basically, you have the two main observational targets, cosmic shear and galaxy clustering, and together you break the galaxy with galaxy bias, and you are able to measure the cosmic growth. But baryons, at cosmic shear, at the smaller scales, I said that they might need to worry about baryons. But there are traces that trace directly the gas distribution, like the Schulze-Seldovec effect or X-rays. If you introduce them in analysis by combining it with cosmic shear, you actually are able to self-calibrate baryonic effects, which from simulations you have very different predictions. But for that, you need this whole pipeline that I was mentioning before. And at the moment, this pipeline, COSMOTHEKA, is actually able to produce all these cross correlations that are going to be useful for this self-calibrating program. So we have galaxy clustering from most of the main galaxy clustering surveys and samples. We have weak lensing, we have CMB lensing, we have CIB, we have TSF, X-rays from ROSAT, and even gamma rays. And we are able to produce the angular power spectra between all of these tracers and compute easily the covariance. And we hope to put this out together relatively soon. But the thing that at the moment, even if it's not publicly available, it's already functioning, and we have used it in several papers.
Sorry.
Yes.
Sorry. Can you repeat the second? So, what is an input? Is the process that is just the catalogs?
The catalog, yeah.
So, in the case of galaxy clustering, it's just
the galaxy positions.
Galaxy position and redshift.
Yes.
Okay.
Yeah. The redshift distributions.
The PDF.
The PDF. No, well,
whatever.
the DND set.
Yeah. Okay. Okay. And for all the others,
But so in this case, will be like a catalog of with the galaxy positions and recifs or recif distribution, similar like the index, also the shapes you need. In the simulation, in this case, we use what they released is if I remember correctly, the ALMs from measured from Planck. So we just use that directly. In the case of CIB, I don't remember. I think it's a map of CIB of different frequencies and different temperatures. I don't remember this. In the case of TSL, something like CIB is one of these maps that Planck releases. And in the case of X-rays, this is the diffuse background of X-rays. I think the map of this is an emissivity and like some intensity.
Intensity, yeah.
Intensity. And in the case of gamma rays, I haven't used it, so I'm not sure, but I will be positions and
Yeah, but how do you account for the fact that they have very different depths?
This is when
in the sense like what, I don't know, gamma ray would tell you about the distribution of baryons or X-rays.
so basically
May be very different from the galaxies that you're observing, right?
yeah. So basically, if you calculate it and they don't have any correlation, basically they just ignore it. Okay. But if you find, so for example, in the case of gamma rays in particular, I was not involved in that paper, but Anya, she's here, or is in Barcelona? In Barcelona. Okay. So Anya, she was working with David and someone else, and it did gamma rays cross-correlated with, I don't remember, galaxy clustering or with cleansing. And the idea was to put constraints on the decay of dark matter, things like that. So even if you don't have a signal, you could use that lack of signal to put some constraints on something else. Okay. But this is just, so what we'll do is, at this level, we just compute the CL. Basically, we just measure if there is a cross-correlation. Then there is the next step, like part of the inference, that would be like, why do I have this cross-correlation? And then you need a model to assume some things and to put some constant. Yeah. So you need a way of explaining that measurement. But at this level, is just measuring if there is a cross-correlation.
Thanks.
Okay. And before moving to showing some results, I would like to highlight that developing this pipeline has been a lot of work, and this not only code development, but also we needed to develop some of the tools that it relies on. So, for instance, as I already mentioned, that the covariance something I did in my PhD, and then Andrina improved. But also important in this paper from Andrina, the way we estimate the cosmic shear noise. It used to be needed that you need to do many simulations to estimate the cosmic shear noise. She proposed a way of analytically estimating. But also because you had that, by combining so many tracers, you end up having many parameters in your inference. You end up being in an inefficient inference or impossible inference. We work also on analytically marginalizing over the parameters that you don't care. Or more recently, like learning directly the likelihood so that we can basically speed up the inference. And as I said, this has been a lot of work, but it has been very productive. So COSMOTHEKA is behind like 17 or 19 papers already. We have done cosmic growth reconstruction using the tomographic technique that I mentioned before. We have done cosmological constraints and assessed different tension between different data sets. And we have also looked even at astrophysical processes, like for instance here, and doing the reconstructing the star formation rate density. But also looking into the effect of baryonic effects in your in cosmology. And I will mention briefly in the next 10 minutes these three works. So the idea of when we started developing COSMOTHEKA was during my PhD, and at that time you have like the DESI tension was it's still important, but at that time it was more important, was more of a hot topic. And it was this disagreement between the measurement of a state that kind of measures the clumpiness of the universe, and from classical structure, and from Planck, from the CMB. And in particular, we were curious about the disagreement between the measurement of the KB 450 and DSGR. And there was kind of a one sigma something shift between both of them. But of course, looking at these points, you see that there is a lot of scatter. But they use different data, but they use different summary statistics, and they use different modeling choices. So you cannot just compare them, because it's very, very easy to introduce 1 sigma shifts in your data if you're not very careful. So the idea was like to go back to the catalogs and reanalyze it at the catalog level, apply the same scale cast, use the same modeling, etc., and see if they are big. In addition, by recomputing everything at the catalog level, you will be able to combine them, introduce new datasets, and reconstruct the growth. And within analysis, again, it would also allow you to increase the constraining power because you have more data. And that's what we did. So basically, in 2021, we released this paper that was using most of the publicly available data. That we had cosmic shear from DSGR1 and KITS 1000. We had galaxy clustering from DSGR1, the DESI survey, that this is the photometric survey that was locating the targets of DESI. It was quasars to have an anchor at early times, and CMB lensing. And you can see on the right, we were covering a huge fraction of the sky. You have the KITS cross-correlated overlap with the DESI legacy survey, so there will be cross-correlations there. And jumping to result, this is what we found. So we have here S8 with a temporal evolution in sigma 8 as a function of redshift. And if we look at the plot on the top, we have like the orange, basically is the constraint from DSGR1 galaxy clustering with lensing, EVOS quasar CMB lens. The purple is the constraint from KITS 1000, DESI legacy survey, EVOS quasars, and CMB lens. The combination of everything is in red, and Planck is in blue. And the first thing to notice is that by having done this analysis in a consistent way, we found that the DS-like and the KITS-like report compatible histories. And this can be seen as well in the last year, but for the sake of time, I will not show it. And the second thing that you notice that the tension that was located here, basically, we always report S8 perceived zero, it can be found at earlier times. And if we look at the bottom, what we found is that the tension was actually driven by shear. If you just keep galaxy clustering cross-correlated with CMB lenses, you find the gray that is compatible with Planck. But if you just keep galaxy weak lensing, you find the green and you have the tension. So the tension, the S tension was driven, at least in this thorough data set, by weak lensing. That could mean like some systematic effects that affect only the weak lensing sample, or if you want like some changes in the lensing potential if you want to modify gravity, although I would not go that far. And it's interesting though that this paper here from Noah Saylor, that using the cross correlation of CMB lensing with LRGs from DESI, they find tension with Planck. So that might not be the whole story. And just to highlight, although you can get when you combine all these data that were publicly available using their modeling, etc., the constraints we found are these. Compared with the other, we found the best constraints for a long time. So about 1% error with a 3.5 sigma tension with Planck. So, and this is just to highlight that in the epoch of LST and Euclid, we might also want to think of ways of combining them together. Of course, the results from the 1% constraints that the KITS legacy has at the moment probably are way more robust than this one, especially because they updated the Russell distribution, etc. But this is just to highlight that we should keep in mind that we can and we should combine future data set to shrink or robust beyond the possibilities of a single survey. And this idea of combining different surveys brings me to the next part of the talk, that is this brief summary of this paper I did with many people that you know here, I think. I think you're familiar with Raul Angulo, with Matteo Senaro and Giovanni Erico, and David Alonso. I guess that maybe you're less familiar, but you will meet him like next week. And the idea here was like to use the public catalogs of DSY3, KITS 1000 HSC, reanalyze them, and go to the smaller scales that we could attempt. So this is the footprint that these surveys were covering. Basically, DS in blue, KITS in yellow, and HSC in red. The way to model the covariance between them was basically we remove the overlapping area so that we don't have to care about the covariance. This is because the covariance that the analytical estimate of the covariance does not apply here. This is a more complicated case because you have cross-corrected noise and etc. So, and this is without almost any loss of signal to noise because DS is so broad. And this is also something that they did in the official analysis of KITS 1000 and DS, and also in a previous paper from Emily Longley. The good thing as well is that in a previous paper, I had checked that any possible cross-correlation between non-overlapping datasets due to the calibration of the residue distribution, because you use the same training sample, do not propagate to the parameters. So by removing this, we were good to go. And then the question was like, what I mean by small scales. And what I mean by small scales is the following. Here I'm showing the relative difference from a fiducial model in the case of DSY3, taken from the official harmonic space analysis of Cyril Du. The reference will be the dashed line, and then I will focus on 3 cases. Let's focus first in the orange case, that is, if you change your model that predicts the dark matter only spectrum from halo fit to H encode, you see that you get a difference about 8%. But it's even worse in the case of you change to different baryonic effects predictions. If you go, for instance, to the extremest case of Illustris, you get suppression up to 30%. So the way that they accounted for this theoretical uncertainty is, okay, let's remove all the scales that would move our contours by more than, I think it's 0.3 sigma. So that way they made their analysis insensitive to these analysis choices. But that means that you discard like 50% of the data vector. So what our idea was, like, following what Giovanni did in DSY3 in real space, was to, instead of using a scale cut of order 100, let's push it to 4,500. So an order of magnitude deeper in L modes, at least. And the reason why we could do this is because Giovanni had trained an embodied simulation that had been baryonified with the baryon correction model that introduces these 7 extra free parameters that we will be keeping free in the next slides, so that we can account for the theoretical uncertainty in our modeling that comes from the modeling effects. He checked that basically this is accurate enough to fit 74 different hydro simulations up to 1%. And we don't have to worry about the dark matter only prediction because BACO-EMU is accurate to 1% if you compare it with embodied simulations. I'm plotting here basically the effect of barring MC, that is the only parameter that weakness data is kind of sensitive to. And this is basically the suppression. And you can see that you get suppressions about 30%. And I forgot to say what MC is. MC is the characteristic halo mass for which half of the gas has been expelled from the gas, from the halo, baryonic phase. So the higher this is, you have a stronger baryonic effects. And I will jump to the results so that we don't run over time. So the idea was, to the fiducial case, we go to Lmax 4,500 that roughly correspond to 2.5 arc minutes. That is what DSY3 considered like was kind of safe. But it was also the smallest scales in real space that they used in the official data vector. And I'm showing here the constraint between S8 and omega matter. And the first thing to notice is, like, by having reanalyzed them at the catalog level in the same footing, etc., HSC, DS, and KITS give compatible results. The second thing to notice is that basically the result on S8 is mainly driven by DS, but you gain something about when you introduce the other samples. But the thing that you gain the most is omega matter. The second question we're going to address is, what's the effect of baryons in our data? And what we saw is that by working on Fourier space, we are kind of more insensitive to baryonic effects, and then our results is compatible with no suppression, or basically at most like 10% within 1 sigma. And in the context of the prediction from different hydro simulations, what we see is that we are favoring those that predict weaker baryonic effects. This is interesting because, for instance, Illustris is what is preferred by measurements of the kinetic magnitude of the but this could be just 3 sigma away. But it's interesting that you have this kind of disagreement. But it also could be that basically we are less sensitive to the data and to these effects just because our data has very large error bars at small scales. What happens if we compare the results with the prediction from Planck within lambda CDM? So what we see is that once we introduce the uncertainty of the baryonic effects in our analysis by marginalizing over the 7 extra free parameters, we find the solid contours. And then the tension is reduced to 1.8 sigma, arguably a tension. In the case that we had in the baryons, we have had like order 2.5 sigma tension with Planck. So it's something that we need to account in our analysis. Like we need to account for the theoretical uncertainty in our modeling to not overestimate the tensions in our models. The second thing that we notice is that marginalizing over baryonic effects do not alter the constraints on omega matter, and that means that we end up having a tension in omega matter of order 3.5 sigma. We did many checks to try to find a culprit of this. We didn't find it, and overall we reported a 2-3 sigma tension in omega matter, taking into account the full shape with the full shape of the posterior with a suspicious net test. But I don't want to highlight that too much, and I would like to spend the last 5 minutes highlighting something. That is that we have reached the moment that we don't gain anything by introducing more data in our analysis. What I mean by that? What I mean is that if you account for your theoretical uncertainty, by that you don't know very well how baryons impact your analysis, and you account for that in the analysis, what you find is that your constraints, as you go to smaller scales, basically do not change. You obtain the same error bars on essay. You are dominated by your modeling. Whereas if you were able to calibrate them, you will still gain something. So this is a big problem because we are going to bring way more data now, but the limiting factor at the moment is the modeling, not the data. And if you introduce a prior on your extra parameters that governs the baryonic effects, you could be able, like this is with current data, you would improve your essay constraints by 30%. But with LSST will be even more, because LSST will be more sensitive to smaller scales, and then it will be more impacted by them, and then it's something that we need to think about. And this is something that relates with something that we are working in Oxford, and is using this very flexible pattern that we have to introduce cross correlations with tracers that of the gas distribution. And in particular, Tasha Ferreira led this paper where we use the cross correlation of weak lensing from DSY3 with the diffuse background of X-rays from Rosat. And then using a halo model, she put some constraints on, she analyzed the angular power spectra, and she put some constraints on this MC parameter that we mentioned before. If you compare my results using the 3 weak lensing surveys, I basically was barely able to say something about the MC. However, see, only with the cross correlation, not even the autocorrelation, she could find very tight constraints. And this was later improved in another paper led by Adriana Laposta, where she also introduced the cross correlation with TSZ, with the thermal Seldovic effect. And then you also find very tight constraints, like the green, for instance. So this highlights the need of introducing this extra cross correlation, because that will let you self-calibrate the impact of baryons without having to assume the prediction from different hydro simulators. Problem, and then we'll finish in the next slide. These works I've showed you before are run with fixed cosmology, and this is because the halo model that we were using is not accurate enough to do an analysis of weak lensing because of the transition between the one halo to halo regime. So we need, as a community, to spend some time to develop a model, analytical or emulators, that can allow you to simultaneously fit the cosmology and the baryons at the same time, because the data is there so that we can self-calibrate our theory. But we need something that is flexible enough to do this. And I finish here. And we are at a very exciting moment where maybe we are, for the first time, seeing a deviation from lambda CDM, maybe the same as in the 1998 with the supernovae. And we might be also, the first time, we might be able to say something about the microphysics of dark energy with current cosmological data. However, this measurement rely heavily on background and linear perturbation level quantities. And we need to test also the perturbation regime. And there will be tons of data from LST and Euclid in the next few years. And in order to take most of them, we need robust constraints that we can trust And for that, we need the robust and fast data analysis methods I mentioned before, but also data from many different probes so that we can test our modeling and also calibrate the systematic effects. And hopefully COSMOTHEKA will be available to do that very soon. Thank you.
Thanks for the talk, Carlos. So actually, I have a few questions, but so I guess the first one would be you showing your compilation of CMB lensing plus here and so on, that there's this strong 3.4 sigma tension, right, with lambda CDM. But now in your 2024 paper, you don't see a tension between Planck and this shear data for S8, right? So essentially sigma 8. So, how do we reconcile the two statements?
So first, the other one has also galaxy clusters. That might change a little bit things. But mainly, apart from is also the calibration of the having marginalized over baryonic effects, right? Like that might also impact a bit. Although I did the test, and the change was not that much because DSG1 data is not as sensitive to them, and the same with KITS 1000. Basically, most of the SL constraints it was driven by DSY3. So although there was, so if you marginalize over baryonic effects, I would need to properly do the analysis, but the other day I was doing it. I think maybe you change from 1% error bar to 1 point something error bar. No, there is not a big difference because DSG1 has much larger error bars than DSY3. Then you are less sensitive, even less sensitive to baryonic effects. So the way you reconcile is like first you are using different data in the sense that you have this extra galaxy clustering that will help calibrate a little bit more sigma 8. And then the data is also DSY1 was a little bit lower. It was predicting a little bit lower S8, if I remember correctly, over DSGR3. DSGR3 shifted the S8 contour towards Planck. So there are two different effects, plus the effect of
Planck. You show that even if you get rid of galaxy clustering, the tension did not change much. No?
Yeah, in that case, yes. But that's mostly driven by KITS in that case. In that case, was mostly driven by KITS, not even that KITS always preferred this lower tension. I think I have a plot that I skipped. Let's see if I can show this. How can I make it big on the screen? Yes. So for instance, here the one with DS basically will be DS 3 10 to point is the orange, and KITS 3 10 to point is the purple. So basically the tension this is in sigma 8 today. So the tension will be mostly driven by the constraint in KITS. That this has been always having the largest tension with Planck. And it's so basically I think this was order 2 point something. This was 2.5, I think it's not 2.8. And when you combine them, basically you're entering more. Maybe if you marginalize over variance, I think it would be like here. So it would the tension would reduce a little bit.
Maybe a follow-up. So you also were showing that in your 2024 papers, you did not see any indication of effect of variance, like in shear. You said that it's because we are not sensitive to such small scales, but that should have just been translated into very broad posteriors in the plot that you were showing. So even in that plot, you were, if you take account the current SC best guess for the baryonic effect, still that would be statistically incompatible.
Say it again.
So essentially, what I'm wondering is how to make sense of, on one hand, of your constraints on the baryonic effects being consistent with zero, but also seem to be in tension with the current SC estimates that would predict a suppression of like 20, 30%.
You mean for instance, these KSF measurements,
or your own X-ray measurement, right?
Or my own.
which seem to be even more extreme than the KSC.
So I think that in that case, first the disagreement will be like 2 sigma, something like that. No, like the illustrious would be like 3 sigma away in that particular parameter space if we go there. So it's not like they are ruled out, but I think the way I interpret this is basically I'm showing here in Fourier space. Then you need to project it, right? And then because your data is not going to be very sensitive to the effect of variance, you can. It's not that you don't. So even if you put a suppression like this, I'm pretty sure you're not going to be very distinguished, very different from the other.
If you are not sensitive,
you mean that this will be like completely broad?
Right, but if you are not sensitive to variance, that essentially means that your posterior on the effect of variance should be very, very broad. But here you're seeing that it's not like your posteriors that blow up. They're actually constraining it to be less than 10% at least 1 sigma. You know what I mean?
I know what you mean. I'm thinking it.
Would be cool maybe to even redo your analysis, but with see if you have a prior now on MC, whether you see would find a best fit, because there also could be projection effects.
It's what I was thinking, because I remember doing the exercise and I have uploaded here, but it's not gonna say exactly what I want to say. Where is this? Yeah. I mean, this is for the best fit that they are not too far apart between another, but you can see that the effect of including or not including the baryonic effects within this 1 sigma. I'm not sure exactly where the best fit lied on this 1 sigma control we were seeing before. The effect is minimal with respect to the error bus. And I did the exercise, but I don't have the plots, and I'm pretty sure, but I will have to redo it. If you do it for one of the more extreme cases as well, you find a very small difference especially if you compare it with the side. So that's why, yeah, probably maybe it's a projection effect more than anything else. In the sense that it's not something that we could extract too much information about the effect of variances. And you basically something compatible with 1 because the effect is basically doesn't matter if you don't introduce it in your analysis.
Yeah, and then becomes sensitive to the exact prior that you have on MC.
Yeah, exactly. Yeah, I think that's what is happening.
Thanks.
Are there further questions? Okay, I think the hour is also already over, so let us thank Carlos again.
Eso no sé si alguna vez miramos, cambiamos el prior.
Sí, bueno, no vimos qué pasaba si cambiamos el how broad the prior was, pero hicimos algún test de. Pero fue poner un prior que venía de Bahamas o por el estilo. No, creo que no cambiamos el ranker.
Por ejemplo,
Es muy bien apagado.
constrain on MC.
No, I have already done it all.
Porque ahora
Gracias.
es una cosa que luego hablamos de otro y vas gracias.
Entonces, al tomar uniform prior en este parámetro, lo dices, imagínate si no tienes constraint para nada, sería un flat. Es decir, que te diría que la probabilidad en cada text de MC es gigante. Sí. Pero para que empieces a ver recién los FX MC tiene que ser por encima de 13.5, por ahí. Entonces, bueno, no sé si empezaste en 12.5, pero si hubieras empezado, por ejemplo, en 10.
Creo que empezamos en lo que era más bajo de X9, por ahí.
Entonces, imagínate, de 9 hasta 13,
Sí que no hay
tienes nada, claro, un efecto. Y de solo de 13 a 15, sí. Entonces, incluso flat prior y preferiría no variance porque
Claro.
ocupa un largo
Sí.
parámetro.
Es decir, justo para el paper que estoy revisando, estaba mirando básicamente el shift que teníamos en S8 al introducir variables. En el caso de el 4500 tenemos un shift de media sigma, de 0.5 sigma. Con lo cual sí hay un pequeño efecto al introducir los variones. Pero pues sí, yo creo que no es... ¿Tú crees que simplemente la cadena se ha movido? No sé, es decir...
O sea, estaría bueno, por ejemplo, de hecho, está eso, vale, un paper, son repetir esto exactamente, pero ahora ponerle el prior de MC que vienen de los X-ray gas functions.
Y ver qué sabe.
Dice, por ejemplo, ver que tu chi-square buen switch de datos. Porque ese statement de que no somos sensibles a los varios.
O sea, yo espero que... Pues por el de este que...
O sea, que no seamos, está bien que no seamos sensibles a los variants, pero eso significa que entonces deberíamos tener no constraints en esta equation.
Esto es casi como sin constraints, ¿no? Es decir,
No, pero cuando ves en el plot, ves que,
claro,
que
ya.
pues, puede ser esto del projection.
Pero incluso mira, este por ejemplo. Es decir, esto es el análisis que hicimos de Bahamas. Y el input era este.
Claro, entonces las error bars también. Pero dijimos, ¿por qué no vemos? O sea, tenemos algún constraint. Si es que no tuviéramos constraint, sería todo.
No, pero es decir, a ver, es compatible con el input, pero sigue siendo compatible 1 sigma point 2
Sí.
con los expresos, ¿no?
Pero en todo caso, Bahamas, ¿no? Entonces, en principio, el current.
Sí, si metes algo como flamenco, como el Lustri, sí debería ser ese un poquito más, pero...
Yo creo que estaría bueno repetir con un...
Una pregunta.
¿Sí?
Estaba buscando a Javier. ¿No sabréis?
Javier, ¿cuánto?
Digo. Perdón. Espurúa.
Está en la segunda planta de este. Pero ¿acaso debería haber un guardia allá a la recepción?
Voy por aquí o por
Sí,
aquí.
sí, por aquí está bien.
Vale, gracias.
¿Qué te decía?
Sí, que metemos un prior y como y te va a favorecer algo que está más bajo, en caso de que sea insensitive, de que es podría ser más o menos el mismo. Si eres sensitive, debería cambiarte el poder significativamente, ¿no?
Sí, que no, por eso de incluso hacer el análisis no como un prior, sino ponerlo como un data, que hablábamos ayer.
Sí, eso es lo que sí, eso me refiero.
Sí, bueno.
Sí, sí.
O sea, para testear el prior está bien, para un paper, de que estos datos.
Sí,
Lo que es sería interesante ver si
ahora, a ver, eso sería bastante fácil y no sé si sería suficiente para un paper, pero fácil sería.
Nunca nadie ha hecho un cosmological análisis en las priors con Casey. Perdón, por ejemplo, bueno, dependiendo del resultado, no sé qué.
No se queda lo mismo.
Pero bueno, por lo menos decir, bueno, estos datos son sensibles o así mejora. Pues bueno, tienes que usa para meter ahí también year 3, sí.
Sí, para actualizarlos.
Y eso por lo menos como un fry, creo que estaría bueno.
Sí, estaría bien, sí, porque...
Después de otro experimento que hiciste que no mejoraban los constraints con el max, quizás si no estamos limitados por los modelos, no por los datos. Sí. No estoy de acuerdo, estoy seguro que estoy de acuerdo con eso.
No, pero es lo que se le... no es lo que les da de aquí.
No, lo que leo de aquí es que la covarianza de los datos no te... bueno, uno, que la covarianza de... O sea, dos cosas. Uno, que los errores de los datos explotan, o bueno, son muy grandes en escalas pequeñas. En escalas pequeñas están...
No, pero si tienes fijo dos parámetros, ¿no?
Ahora es que
sí, mejora, ¿no?
un factor 8 tiene 64 veces más modos y bajas en un 20%.
Sí, pero me refiero que cuando marginalizas, toda la...
Es peor.
Claro.
O sea, pero bueno, pero ganas algo proporcional entre marginalizar y no marginalizar.
No, si marginalizas no ganas nada, ¿no? Es decir,
sí, bueno,
Bueno, el segundo es el proceso que
El Omega Mater.
El Omega Mater sí, el Omega Mater gana siempre. Eso, porque sea projection of
Pero
vectors.
te digo, entre marginalizar y no marginalizar. En el caso marginalizado, si ves como el fear of merit, aumenta algo que no es tan diferente.